section 2 of chapter 7, you start dealing with use substitutions of definite integrals. Before I show you some examples, let's review some of the notes for the use substitution. So the basic idea behind the substitution method is to find a way of reversing the chain rule. Some steps for use substitution. Remember to look for an expression for u, so let u equal an expression so that du is similar to the rest of the integrand. This is using the method that Mr. Patrick JMT showed you guys in the previous video, the one before this one. So this is kind of using the Patrick JMT method. Step 2 is find du, substitute in u, du, and integrate, and substitute the expression for u back in for u. So although I kind of laid out these steps using the way you learned it with Patrick JMT, you can remember what I said in class. You can still do it the method that I showed you last semester, or if you like this method that you learned in the previous video, that works too. Alright, so let's go ahead and try this example. So notice that we are integrating with limits now. So this is a definite integral. So the integral from 0 to pi over 3 of tangent secant squared dx. So I'm going to have you guys pause the video and tell me what you would let u equal. And remember that the key is to let u equal a function whose derivative can be found within the integrand also. So in other words, we have tangent x and we have secant squared x. But we know that if we let tangent x equal u, or let u equal tangent x, then the derivative of tangent x can also be found because it's secant squared x. Oops, this the x. Oh no, I'm sorry. That was right. The derivative of u with respect to x. Okay, and you split this up. So after you do your work, dx is equal to 1 over secant. Well, let's do it the way that Mr. Patrick JMT did it. So secant squared x dx is going to be substituted for du. So after you plug in your values, you now have the integrand from 0 to pi over 3. Now that we have a u, that's what we let our use substitution be, and then this part is du. Okay, now when we're integrating definite integrals and we're doing the use substitution, we always have this problem. We started with x values for the limits, so if the original problem was in terms of x, so tangent f secant squared x, the limits are x values. So that's x equals 0 and that's x equals pi over 3. So we have a problem here because technically we have x equals 0 and x equals pi over 3. However, we have a function in terms of u. So we need to fix that. We're going to fix that by changing the limits to values of u instead of values of x. So to do that, we need to take our lower limit and our upper limit, and what we're going to do is we are going to use u equals tangent of x to change these x limits, these limits that are in terms of x, or that are x values, we're going to let u equal, we're going to use the u equals tangent of x to change them to u values. So we have u of 0 is equal to tangent of 0 So all I did was I plugged in x equals 0 here, and if you remember from the unit circle, tangent of 0 is 0. So this implies that my x equals 0 stays 0. So my lower limit of x equals 0 stays 0 for u equals 0. Okay, we have to do the same thing, but now with the upper limit of pi over 3. So u of pi over 3. We're still plugging it into tangent of x, but now it's tangent of pi over 3. And if you remember that from the unit circle, we get radical 3. Now, this implies that my upper limit of x equals pi over 3 will change to u equals radical 3. So, finally, we have, so we're going to take this now and we're going to change the limits to 0, or from 0 to radical 3 of u du. And the rest is pretty easy. Go ahead and just apply or integrate that. So integrate u squared, we get u squared over 2 from 0 to radical 3. You guys finish this, pause the video, and finish this, and I'll show you the answer right now. So I pretty much left you off where you had to apply the fundamental theorem of calculus, and after you do all your computations, you get an answer of 3 over 2. Okay. Let's go ahead and try this problem. So again, just like we did the first time, let me have you guys pause the video and try to find your u substitution on your own. So notice that we have x squared plus 1 cubed and x. If we let x squared plus 2 be your u substitution, x squared plus 1, then du dx, the derivative of x squared plus 1, which is 2x, can kind of be found in the integrand here. If we were to multiply this by 2, it's kind of there. So that's a good indicator that x squared plus 1 should be your u substitution. I'm going to go ahead and do this one the old-fashioned way, the way I showed you guys. So du is equal to 2x dx, and dx is equal to 1 over 2x du. So when you integrate, or when you plug this back in, we now have the integral from 0 to 1 of x u cubed, and then for dx, I'm going to plug in the 1/2, or 1 over 2x du. And you see that the x's will cancel out, and the 1/2 will come out as a constant. So we have the 1/2 that comes out, 0, 1. the u cubed and the u. Now, before we go ahead and integrate this, we need to change the limits. So we need to change the limits. That's not how you spell change. And we're going to change the limits by using the u substitution of u equals x squared plus 1. So when x equals 0, let me have you guys do this and match it up with mine. Pause the video a little. So here we have the new u values for the limits. So when x was 0, my new lower limit is going to be 1, so that'll go there. When x was 1, my new upper limit will be 2, and that'll go there. So now what we have is 1/2 times the integral from 1 to 2, and it's u cubed du. Okay, so you guys go ahead and integrate this. Again, pause the video and finish this off and check with mine. And after you apply the fundamental theorem of calculus, do your computations, you will get the answer of 15/8, and that is the answer. Alright, that is it for this video.